Hi guys, so this is week 11, video number 1, and last week we had 3 videos on alkanes and alkenes and also an introduction to OChem, organic chemistry, and we're going to continue our discussion with alkenes today, and the focus of the first page of our notes is Cis-Trans Isomers, alright, Cis-Trans Isomerism. So the definition of Cis-Trans Isomers is they have the same formulas and connections between atoms, so they look almost identical. They have the same formulas and connections between atoms, but they differ in their attachment to the different sides of the double bond. If you remember, alkenes have a double bond, a carbon-carbon double bond, and that is a rigid bond. It doesn't freely rotate and swing like a single bond does. So because of that, we can have cis-trans isomerism. So here is 1-butene, and I'm drawing it out. And you see that on the left-hand side, the way I've drawn it, the left-hand side of the double bond, there's 2 identical attachments, happens to be 2 hydrogens. So if I were to flip-flop those, it would look the exact same. See how the bubbled H's, they'll look exactly the same if I flip-flop this. So these are actually the same compound. I'm unable to have cis-trans isomers for an atom, for a molecule like 1-butene, a compound, okay? Compounds like 1-butene is just not going to have cis-trans isomerism. We have to have a certain requirement has to be met regarding the double bond, and I'm going to show that to you now. If you look at 2-butene, look how I've drawn out 2-butene. You see how each carbon in the double bond has 2 different types of things attached? Well, here I have cis-2-butene. That's where the larger substituents are on the same side as each other. Now the trans version, I'm going to have the CH3s like this on the opposite side. Here's the double bond, and they're trans, like transcontinental. So transcontinental, opposite sides of the country. Same thing here with the larger substituents, that being the CH3 groups on opposite sides of the double bond. Okay, so top of page 2 of our notes here, it says, example, which of the following exist as cis-trans isomers? Draw both. So I'm going to have to kind of expand here. 3-heptene, I've got to draw it out, so I do 7 carbons. I put my double bond on carbon 3, and I'm circling the attachments to the double bond. Each of the carbons has 2 different things attached. All right, so yes, I can draw these as cis-trans isomers. The cis version is going to have the H's on the same side, or the smaller substituents on the same side. And then I draw the 2 larger substituents down, that's cis. If I draw my H's across from each other, like the one on the right, or if I draw my larger substituents across from each other, like the one on the right, then I have trans 3-heptene. And you see how I put the cis dash, trans dash, 3-heptene. All right. Now let's take a look at B, 2-methyl-2-hexene. All right, so I have to draw this first, and I can just draw the skeletal structure to get started. And the bare bones structure, I see, the carbon on the left, the double bond carbon on the left, has 2 of the identical CH3 groups attached. So I'm not going to be able to have cis-trans isomerism. The answer here is no. C, 5-methyl-2-hexene. Draw the backbone out. I put my 2-hexene skeleton in, put my 5-methyl group in, and then I circle all what are going to be attachments to the double bond, and each carbon of the double bond has 2 different things attached. Yes, this is going to work. Now let's draw them. So in the first one, the cis isomers I've drawn on the left, I've either got the 2 H's on the same side or the 2 large organic groups on the same side going down. And then on the one on the right, I've got my H's either opposite, like I'm drawing here with my hands, or I've got the large organic group and the CH3 group opposite like that. So the one on the left is cis 5-methyl-2-hexene. The one on the right, trans 5-methyl-2-hexene. All right, so that is cis-trans isomerism. All right, now I want to switch topics. We're still on the topic of alkenes, but I want to switch topics away from cis-trans isomerism of alkenes and instead talk about the properties of alkenes or alkynes. Remember, alkenes are when you have the carbon-carbon double bond functional group. Alkynes are when you have the carbon-carbon triple bond functional group. So we're just going to do a very brief list of properties of alkenes and alkynes, something to consider for multiple choice questions, fill in, etc. Alkenes and alkynes are less dense than water, which means they would float on top of a layer of water. They're insoluble in water. They are immiscible or hydrophobic. They tend to be flammable but non-toxic. Alkenes, that's the carbon-carbon double bond, they can display cis-trans isomerism. We just saw that. You have to have each component, each of the two things off of each double bond carbon would have to be different from each other. Now, chemically, they are reactive at the double or triple bond. That's why it's called a functional group, right? It controls the function of the molecule in reactions and stuff like that. So the double bond and the triple bond, those are the hotspot areas of where reactions occur. Speaking of reactions, I want to talk about three. I want to talk about hydration, hydrogenation, and halogenation. The first one, these are some addition reactions of alkenes and alkynes. We will focus almost exclusively in this class on addition reactions of alkenes. Hydrogenation is the addition of H2 across a multiple bond. So across a double bond here in my example, alkene plus H2 and then some sort of catalyst, maybe palladium or platinum, sometimes nickel. Basically, you're just adding H2 across the double bond. The single bond remains, and now you have two extra hydrogens, which would give you an alkane. The alkyne, you'd have to do this 2 times to get all the way down to the alkane. So you'd have to add 2 H2 to get your alkane. All right, that's hydrogenation. So, as an example, here I have a alkene ring, so I have a cyclohexene, and I'm going to add H2 to this. Palladium is just a catalyst. You can ignore it as far as drawing. You're not going to ever draw palladium or platinum into a product. So basically, I'm adding H across the double bond. You see I've now drawn 2 extra H's and the double bond is gone. And I've just drawn the molecule 2 different ways because we're new to some of these structures. Now, B is halogenation. It's the exact same as hydrogenation, except you're not adding H2 across a double or triple bond. You're adding Cl2 or Br2 across a double or triple bond. As an example, here I have ethene, which has a common name, which is ethylene. If I add Cl2 here, as you might expect, the double bond goes away, and I've added 2 Cl's to each of those double bond carbons. Okay. So the product here, we should know how to name. It's 1,2-dichloroethane. All right. Now, we will get to C, hydration, later on. So there are 3. I've just covered hydrogenation and halogenation at this point. Some random examples. Example, write structures of products for the reaction of the following. So the first one, A, I want to write structures of the products for this reaction. Cis-2-butene plus H2. Okay, what's that going to give me? Well, I'm going to get rid of the double bond by adding H2. All right? So basically, the cis-trans isomerism goes away the minute the double bond is gone. So if you look at my product, the 2 H's in bubbles are the ones I've added. And then if you draw it properly, the only way to draw the right answer is to draw it as I have in the box there, butane. So B, now we have 1 pentene plus Cl2. So we should draw the backbone for pentene. So I got 5 carbons structure with a double bond at carbon 1, like 1 pentene suggests. Then you put your Cl2 on those carbon 1 and carbon 2, and then you fill the hydrogens in everywhere, and you come up with this answer, 1,2-dichloropentane. All right, and notice that's all one word, 1,2-dichloropentane. All right, now I'm going to cover that third one. This is the third box. I did hydrogenation, halogenation, and this is hydration. This is the addition of water, okay, as it suggests. Hydration, addition of water. Kind of focus it in on the fact that you're really adding H and OH to each of those double bond or triple bond carbons. Now this follows something called Markovnikov's rule. In an organic chemistry class, we would go into more depth. I'm just going to give you the definition in a workable form. It says, in the addition of HOH across a double bond or a triple bond, such as an alkene or an alkyne even, the H, because you're adding water, right? So you're adding H-OH across a double bond or triple bond. The H is going to attach to the carbon that already has the most hydrogens on it. So just think about putting the H with all his friends, all of his other H buddies. Okay, so the hydrogen attaches to the double bond or triple bond carbon that already has more hydrogens. And then the OH will go to the carbon that has fewer hydrogens. Best to show an example here. So I have two CH3 groups on the carbon on the left, and then on the carbon on the right, I just got my two hydrogens. So if I have water, the H is going to go to the carbon on the right, and the OH will go to the carbon on the left. See how I've drawn it? Okay, so this is how I've drawn the result of a hydration of an alkene. All right. Now, I put a box around the major product. That's called the Markovnikov product. The other product doesn't even form, or doesn't form to any great extent. All right. So the only product for us, the only product is the Markovnikov product. And then I'm drawing it all over again just so you can see it. I just tucked that far right hydrogen into CH3. All right, let's do another example. It says predict the products. All right, so the instructions are simple. Predict the products, which means I'm going to have to look at the reactant and the reagents. So the first one is going to be a hydration reaction, A. B is also a hydration reaction because we're adding water across the double bond, which means we add an H and an OH across the double bond. The H goes where all his buddies are, where more hydrogens already are. That's why you see the OH on the ring carbon. And in the second one, I put the OH on the one that has less hydrogens, and I put the hydrogen, see my little dot, 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 H, really, really faint? That's the hydrogen from HOH that went there. All right, so that's it for alkenes and alkynes. We've now covered alkanes, alkenes, alkynes. Now, aromatic compounds. This is the last of the 4 hydrocarbons that have nothing but hydrogen and carbon in them. So aromatic compounds, these are compounds that contain benzene and or benzene-like rings. A benzene ring is a 6-carbon ring with alternating double and single bonds. Okay, and I don't want to get too much into it, but the double and single bonds are in resonance with each other. So every bond is essentially like 1.5 bond. It's not a true single bond or a true double bond. It's kind of right in the middle because we have this thing called resonance where the double bonds and single bonds kind of flip-flop. So that's kind of what the dot, dot, dot means. And then when you put the circle, okay, you see the box I have there where it says benzene? That is just the circle, just means that the double bond in the ring spends half its time in each of the single bonds. All right, so aromatic compounds are cycles, okay, they're rings, and they have alternating double and single bonds. It's not just a ring with a double bond in it, all right? Now these guys are very unreactive because that benzene-like ring is very, very stable, and he doesn't want to interrupt the off-on double bond, single bond cycle. They want to keep that. So things like hydration, bromination, hydrogenation, there's no reaction here. And we just saw that alkenes and alkynes would react. All right, so let's talk about naming aromatic compounds. All right, first one I've drawn there is a benzene ring with a bromine on it. So it's called bromobenzene. The second one I've drawn is a benzene ring with an ethyl group on it. It's called ethylbenzene. Third one I've drawn here is a benzene ring with an NO2 group. That's called a nitro group. So this is called nitrobenzene. All right, those are monosubstituted. Now let's see some disubstituted benzenes. All right, disubstituted benzenes are when you have a benzene ring with two things attached. We can do a 1,2 substitution where they're attached right next door to each other. 1,3 substitution is called meta. So 1,2 is called ortho. 1,3 is called meta. And a 1,4 substitution or a 1,4 disubstitution is called para. So you'll see these in your naming. You need to be aware of them. All right, let's do an example. All right, I have a benzene ring here with a bromine and another bromine right next door. That's ortho. This would be ortho dibromobenzene. Sometimes the ortho is abbreviated with just an O. O dibromobenzene. So it's ortho means right next door. 1,2. Next example, I have an NO2 and a Cl, and these are a 1,3. 1,3 substitution on the ring, which means that they're meta. This is meta chloronitrobenzene. All right, C comes before N. That's why it's chloronitro, and I've underlined the C and the N for you there. Meta chloronitrobenzene. Next example, I have a CH3 on the top of my benzene ring and a fluoro on the bottom. So this is para. 1,4, right? Number the ring anywhere you want. The substituents are 1 and 4. So this is para-fluorotoluene. Why did I call it toluene? Well, toluene is a benzene ring with a CH3 group on it. Okay, that is apparent. You could also call it para-fluoromethylbenzene. All right. So in the next video, we're going to continue with see what I've just done basically is I'm now finished with your chapter 11, and the next two videos are going to concern themselves with your chapter 12 in your book, which are going to be things like alcohols, ketones, aldehydes. All right. So I'll see you in the next video.